Right. So again, I would like to warmly welcome Alan and Amor to share with us about Sugarcrete. Uh, I'm not going to drag on anymore. I will just pass it on to the both of you. Welcome.
Great, thank you very much. We've decided to split into two halves, so I'm going to do the kind of why, and then Amor's going to do the how. So we're sort of 50-50, so we can take questions afterwards. There's quite a lot to say, so if it overruns, sorry, and if I cut too much off trying to get in time, then also just ask questions if there's anything that is needs clarification. So I'll just share my screen and we'll have a little look at what we've got. Okay. Hopefully everyone can see that. So yeah, it's a global material for a global crisis. So we've done this work over the last kind of 4.5 years, and it's kind of generated a kind of certain kind of impetus. So it's always nice to kind of go back over it and just try and explain kind of what we've done, how we've done it. So these are the folks that are kind of in charge of it, I guess you could say, although it's more like sort of skiing rather than driving. So you kind of have to zip round trees and rocks and stuff as you go downhill quickly rather than being in total control of everything, which is kind of what innovation is about. So hopefully through this little presentation, you'll get a sense of what we've done and the things that we've done, and then maybe that's useful for people thinking about innovative new ideas and the kind of steps that you will then realize you have to take to get something somewhere. So we look at the problem, right? So the problem is a big hole in the ground. Building and construction sector, we've all decided to become architects, and that's possibly one of the most damaging professions we could have chosen to join. We can see that it's a bit of a big issue. So therefore, we need to think about not doing architecture, but how we do architecture and what we do it with. Obviously, we have this target from Paris, this below 1.5 degrees C, depending on where you look. We've already exceeded it by twice, but that shouldn't stop us trying to make sure that we can keep it down again. So part of what we're doing is obviously related to this issue of carbon and climate change, but that's not all. So we'll see a little bit more about what we're interested in as we go forward. So our usual default position is, hey, let's build in timber because that's good for the planet, right? I hate to spoil that for everybody because that's not necessarily the case. What we understand by timber construction these days, it's actually a pretty northern hemisphere sort of phenomena. The kind of fast-growing pine-related timbers that we use are pretty much concentrated in certain places and not others. And so if we start cutting the trees down in the global south, they're usually connected to rainforests, which is an extremely bad idea. So the kind of timber production that we're used to globally is pretty much a northern phenomena, which doesn't really help much because most of the global growth is going to be happening in the southern hemisphere. So the question for us then, if timber is a slight problem, and we'll talk a little bit more about that later, can we upcycle globally what we're going to be growing anyway, rather than simply growing trees? So this is a big question for us. This is what sort of set us off on our journey of exploring agri-waste. And there are certain questions that one needs to ask when one starts exploring agri-waste. One of which is how much of it have you got? And the other one is, what exactly is your enemy? What are you trying to replace? What's the innovation actually seeking to do? Our work in India is illustrated by these two slides. If you want a brick in India, you will get one from one of these kilns. They are either fired by coal dust, which you can see what happens when you fire things with coal dust, or they're fired with biomass, which is residues from farming. We've seen both in action in India. The end result is what comes out of the top of the chimney. So we have some issues in terms of pollution, in terms of air quality, and also in terms of the lives of the people who actually do this work, which when India's hitting 50 degrees in the summer, you don't want to be standing on top of a furnace, but people do. On the other side of this slide, you see the bio-waste. This is one of the pictures that we've taken from the residues from the sugarcane industry. India is the second largest producer in the world, and it produces quite a lot of this stuff. So if we're going to tackle a very large industry of brick making, we also need a very large amount of stuff to tackle it with. So when we're talking about amounts of stuff, what do we really mean? We've done this diagram, which looks really exciting, but probably incomprehensible. So I'll do my best to unpack it for us all. So on the left, we've got the total production of collectible agricultural residues. Okay, that's all the stuff. You can kind of see it in there as maize and rice husks and bagasse. It's all added up. And out of the 6 gigatons of wet matter, you'll probably get 4.4 gigatons of waste. And that's split up into these various different residues. And then we start looking at what happens to them. So on the right, we see that 2.3 of those gigatons is just burnt because it's just a waste product, completely useless. Then we have a series of gigatons worth of active use, which we could say is kind of valuable. It has value. And so what we're looking at is how can we extract some of this waste? And if we did, what would the results be? So if we only look at the stuff which is kind of waste, doesn't have value, it's not generating electricity or doing anything, kind of feeding cows or doing something useful, we end up with still the 2.3 gigatons just burnt. We've also got nearly half a gigaton of stuff that's just left in the field to rot. So with that 3.25 gigatons, let's see what we can do with it. So if we compare it to industry, and we're looking at purely on weight, we've got bricks, which is 2.18 gigatons, and insulation, which is a tiny amount of gigatons. So, but those two products end up at being $94.6 billion worth, right? So if we can divert some of this waste material into bricks and insulation to the value of $94.6 billion, you can see in terms of tonnage, we've got plenty to spare, right? So if we can simply divert this useless waste into these $94.6 billion worth of product, then we might have an idea. And alongside that, in terms of money, we've also got the carbon. So we've got a lot of carbon being generated in this dry matter that is able to be held. And if we can secure it in construction materials, in buildings for 50 years, then we're doing a pretty good job. We're not releasing it. And that is the key thing that we're looking at. So how we can bring these things together in a kind of sensible fashion. So looking at sugarcane, there was a kind of an accidental reason why we looked at sugarcane. We're based in London. We don't have a lot of sugarcane in London, but we do have right next to our campus quite a lot of sugar because it's the Britain's largest sugar refinery. Is I can see it from my office window, kind of. So we began to look, thanks to our more students actually, at various waste streams running around the campus 4 or 5 years ago. And then sugar pops up. So we begin to look at the residues of sugar. Our sugar refinery doesn't have the fibers, it's simply got the juice extract. But we began to kind of dig around. And so you begin to look at the nature of the waste products. You get about a third of the sugarcane left over as this kind of dry fibrous stuff. And you get quite a lot of it. You get 624 million tons of it. And as it's very lightweight, the size of that tonnage is quite incomprehensibly large. As you saw in the photograph I showed earlier, you're talking about mountains of it, literally. So with that amount of bagasse, you could replace the global brick industry. And that's therefore viable, because a lot of the kind of biomaterials that we come across are basically pretty small scale, and it doesn't kind of work for the amount of capacity that we need for our building materials. You know, we're going to be getting on 9 billion people. It's going to be multiplying. There's going to be development right across Africa and Asia that's going to require building materials. How are we going to supply that need, let alone kind of repair the stuff that we've already built? So this is the amount you get. You get 20,000 kilos per second, which is 72 million bricks. You can make those during Armour and mine's presentation today, and that's about 10,000 80 square meter houses worth of bricks and insulation. So yes, just count those houses as we speak. We do look at the other biomaterials. I mentioned the fact that their sugarcane is far bigger. So what do I mean by that? Here's a little graph that shows you what I mean by that. Hemp is very fashionable for many reasons, but you'd have to really multiply by 16,000 times to get the amount of bagasse that you've got. And that's sort of the size of the UK. So if we got rid of everybody and started growing hemp in the UK, flattened every city, then we could probably match our bagasse supply, but we're not going to do that. So one of the advantages of sugarcane over hemp or some of these other plants is that it grows so quickly. And it grows so quickly that it's around about 50% greater CO2 absorption than traditional forestry, back to this forest story. And it's 20 times higher than hemp. So we've got something that's very efficient. Yeah, I hate to bang on about timber, but I used to like timber buildings. I still do, but it's a bit of a problem. If we've looked at it in terms of carbon. We're starting to look at it in terms of money, but maybe you also need to look at it in terms of land. So if you have a CLT wall, 20 centimeters thick, a square meter of it will require nearly 11.5 square meters of forest. And bear in mind that forest will need to be there for 35 years, more or less, to get the timber out of it. If we looked at a timber frame wall to save a bit of timber, because CLT is solid, then we can get it down to 5 square meters of forest, which is pretty okay. But when you look at a Sugarcrete wall, you only need half a square meter to produce that wall. So in terms of land use, it also is incredibly good. We have been looking at some data coming out. Built by Nature have produced some reports showing that you're only really getting 10% of a tree to actually secure carbon. The rest of it kind of gets wasted, blown away, burned, whatever. So if your tree is only delivering 10% of its mass as a carbon saving element, then that's actually not really a good return on your 11.4 square meters of forest. We have our engineer colleagues, AKT2, have kind of calculated, just looking at the log, forget the leaves, just look at the log of a tree, you're only actually getting kind of 30% of that tree trunk as being useful for carbon. So we're really looking at a lot of wastage in the forestry industry. So for us, it's not the silver bullet to solve this carbon problem. So goals and strategy. Yes, how academics love to talk about goals and strategy. Anyway, to store the carbon absorbed during sugarcane's growing cycle, we need to stick it in something for a long time. So I'll talk about carbon credits in a second. So what we also need to do, because we're proper architects, we think about people more than we think about buildings almost. We need to develop a material which is going to be of benefit to society, not simply through carbon terms and money terms, which often ends up in very few people's hands. How can we also share the knowledge? How can we begin to try and promote the use of this material that we've come up with so that it's open source as much as possible? You can share it with communities. They can transition from being virtually enslaved to brick kiln owners. And how can we kind of open this up? So there becomes the sort of social question as well. And obviously these things need to perform. So we need to be able to validate their performance. We need to be able to benchmark biomaterials against conventional materials, which is very difficult because all of the testing that goes on has been developed for traditional materials. I say traditional, like the last 150 years, steel, concrete. So what we need to do is to be able to get our heads around that whole kind of certification question as well. So effectively what we're doing is taking this linear process of sugar, which is this production, harvesting, production, and some of which being burnt for value, and taking the stuff which doesn't have value and making sure that we don't release these chemicals into space. What this is also telling us is where the production of Sugarcrete ought to happen, because clearly if you're generating the bagasse pretty close to where you're growing it, then we are looking at a global south solution, a kind of an equatorial sugarcane belt solution, rather than one that's fixated in Europe, because that's not the center of the globe, believe it or not. So when we start going kind of circular about it. I notice on our map we're still in the middle of the globe. I think we need to change this. What we need to do is to look at this kind of whole cycle. So diverting some of the materials, producing the materials with as few additives as possible, so that it's as simple as possible, as traceable as possible, making construction materials, making buildings which can be put together such that you can reuse those materials as often as possible. And eventually, when you can't reuse them anymore, you have a product which can be ground up and become a soil improver back to the fields. The interesting thing about the brick industry is that they're basically excavating the clay just below the topsoil, allowing you to not really grow your plants on it anymore. So in India, the brick industry is stripping out all of the clay from the ground, depleting its own ability to grow crops. So really we need to get a grip on this one. Circularity. So this is a photograph of one of the machines that we've developed with our partners in India, Chemical Systems Technologies. They jumped on what we've been doing with our communications and contacted us and basically invested in making a building that we could test. Using materials, using equipment that is incredibly simple so that it's as shareable as possible. You can buy this equipment from our partners if you want to set your own factory up. That's the whole point, and then you get supported to manufacture. That's the plan. Talking of connections, India has been our most energetic connection, but we have a series of others. This map is still out of date now. Trouble is we'd spend our entire time updating our map if we did it. So we're basically speaking to people all over the place, and some of these conversations are turning into work that we can actually consider impact. So in order to sort of facilitate that, we've had a series of kind of bits of legal paper to try and make it work, and we've got a sort of process now where we can begin to go from initial conversations through non-disclosure agreements, through memorandums of understandings that are linked to an ethical policy, which we've written. And then we're making project agreements on a case-by-case basis with the intention of creating buildings. So we're into our second building now. We've got several others starting to pop up like mushrooms. So it's become quite a successful, if slightly interesting process. It's a thing in itself. It's the material science suddenly turns into law and IP and all that. But architects are used to that kind of paperwork stuff. It's what we spend most of our time on, after all. So the testing to industry standards is critical. No one's going to buy it. No one's going to believe it unless you can show you pass a test. So the value of being within SRI is that we have our own labs. So we know what we're going to get before we have to then get a lot of funding together to pay lots of money to certification laboratories. The plan is to become a certification laboratory. And once we can do that, then we can certify what we're doing. So this is some of the kind of the basic performance criteria that we're looking at. On the left photograph, you can see that the first thing we did was make a cube of it and try to burn it to bits in the metalwork lab. That obviously was interesting because it did burn. So therefore we carried on. If that thing had gone up in flames, we'd have given up at that point. So the first thing to do is to understand kind of the idea that you've got, to try and validate it, to make sure that it's sensible. Then you can pour the energy into getting the pieces of paper. In terms of fireproofing, we've ended up doing a 3x3 meter test in a furnace where we ended up with 1100 degrees on one side of the wall and 25 on the other, and for 4 hours. So that proved that the thing works, and the rest of the world can see that it works. This kind of process is integrated into our Construction Week program for teaching, which is about sharing this understanding of how do we get things to perform. So it's not just a bright idea, it's also hard work. So we've got all this equipment in the labs. We always show this one because we quite like the idea of just setting fire to something and seeing what happens. But beyond that, we then throw a whole load of other bits of equipment at it to make sure that we've got that ability. And we train the students in using some of these bits of equipment in our Construction Week work. So the overall performance of the material, it's a technical performance, but it's increasingly important that it's a life cycle issue. because as legislation transforms and we have to begin to account for the specification of materials that we make in our buildings, we have to track that, we have to show that it's from ethical sources, we have to look at the entire life and death of buildings and understand the carbon impacts. That will be a requirement as part of our architectural design process. So looking at the life cycle analysis, we can begin to see where it sits. We can break down the amount of carbon that it's sequestered versus the amount of carbon that it's used. And we can see it in comparison here to concrete blocks or clay bricks. So it's 3 times better than a concrete block. Carbon credits are an interesting phenomena. They're slightly dubious, looks like a kind of capitalist cartel. However, it's an existing process whereby people can offset their carbon by investing in people who've secured carbon, and by planting forests or whatever, you will be able to invest in a Sugarcrete brick. It has an amount of carbon. You can see there that if we replace clay bricks or concrete blocks in a small building, we'll save 120 tons of CO2. You can purchase that CO2 from our building, from the owner of that building. And that means that the owner of the building who's bought the Sugarcrete blocks gets a subsidy, and that effectively brings the price of the bricks down. So that means that we don't have to charge as little money as possible for our bricks, meaning that we've just employed people on low wages. It means that we can pay people properly, and the act of getting carbon credits on each block allows you to effectively bring that price down. So we're trying to make sure that the blocks that we can make are competitive with the business as usual materials without kind of leaning on the workers to pay them less, which is the usual capitalist story. So we're throwing the kitchen sink at trying to get innovation to work and trying to make architecture that is better. Armour will show you some of the results of the architectural moves that we're using our materials for. But this is just a kind of quick kind of run through of who we've talked to and how we've talked to them. Just so that you can kind of get a sense. So I'm setting you up for Armour's kind of like far more visually appealing set of photographs. I don't know why he always gets the good jobs, but anyway, whatever. So it really started back in 2021, where we're doing these kind of construction week workshops, working with Tate and Lyle, and working out just how we can make this thing happen. So we did a project with Grimshaw Architects, which we learned a lot from. It got a series of kind of impacts. Armour will show you some of that. That got us a decent kind of design publication, which started to attract attention globally. We're getting sponsorship from the raw materials from Tate and Lyle. We're doing follow-up workshops and starting to develop new kinds of binders that work with the Sugarcrete. At the same time, Armour gets on his Instagram account. So we're starting to build a kind of conversation globally. We also obtain a trademark for Sugarcrete, which is why I've got the little R after it. That's important because in terms of intellectual property, it's very difficult with a material that's deliberately simple to try and protect it, because it's so simple that anybody can do it. And therefore, holding on to your IP is very difficult. However, the name Sugarcrete is quite cute. None of us can quite remember exactly who came up with it, but that's fine because we're not in a competition here. So all you can do is to build the brand, right? And if it's not Sugarcrete, we don't want it. So our only protection really is the name, and that's why it's important to have that name protected. We start working with chemical systems technologists towards the end of 2022, and they say, let's just build a building then. And we go, okay, let's get on with it. We got a Shop Prize nomination, which was kind of cute, and we get more publicity. So people become more interested in what we're doing, and a lot of what we're doing is generated by the students themselves working with us in the labs in Construction Week. So teaching, people call it kind of research-based teaching. It's teaching-based research, actually. So I think I turned that one around. So we're looking at this kind of process, and then more and more people get involved. So the chemical systems technologies guys are friendly with the sugar mill owners. We begin to locate the construction there. We begin to understand a lot more about all of the waste streams that are coming out of the sugar industry. We start signing MOUs with people. We start doing joint ventures. We bring some of those people into Horizon grant applications that we're doing. We won the Times Higher Education Award for innovative knowledge transfer exchange. We won a Built by Nature award and the funding from that and our higher education impact funding money has also enabled us to do a lot of this actual contact work with people. And that kind of feeds the cycle. So you end up with this system where the PhD students start coming in to look specifically at these materials. People want to come and study with us to really push that. They become integral to the practice of making the science work. And so it becomes a little bit more fun. I think we need to update this one again, because the last year has been kind of like quite exciting with real projects being commissioned for us to begin to design again with the student support. So I'm going to now hand over to Armand, who's going to talk about exciting things. Over to you.
Thank you very much, Alan. Hello, everyone. Let me just go to the slide where we start to talk about the projects that you have done. Can everyone hear me okay? Yep, perfect. So let me just share the screen. So Alan has done a very good job describing what are we doing and how are we doing it. And I want to show the results of some projects that we have developed, all of them in collaboration with students from the University of East London through live workshops, which we develop at the beginning of the academic year. So it's the first thing that the students do when they arrive at the master program of the University of East London. They have 2 weeks where they immerse themselves into construction, into building prototypes at one-to-one scale, and then they report and document that building process into a set of reports. And they do that in collaboration with external partners. So from the beginning, we believed that this was something that we couldn't do just looking at the work that we do internally. We need to look at what other people are doing outside and how we can collaborate with them. So all the projects that I'm going to show, they all have external partners that are collaborating with the University of East London, the Sustainability Research Institute, and the Master of Architecture program coming together with prototypes and ideas to then implement in real-world applications. Some of them had different impacts, and we are now doing an exercise on assessing how do we assess success for ourselves, whether success has to do with social impact, media impact, economic impact, or academic impact, which they are very different. Sometimes they are interconnected, but very often the same project doesn't fall in the same category. And I will try to highlight what do we think that we achieve with each one of these projects and how it relates to the next one that happened. The first one, which we did back in 2023, it was called Sugarcrete Slab, and it was a collaboration with Grimshaw Architects, an architectural firm based in London, but with a presence globally. AKT2 Engineers, an engineering firm, again based in London, but working in different countries across the globe, and they have been collaborating with us since in the project. They are actually coming today to the university. And Data Lyle Sugar, which, as Alan mentioned before, is a sugar refinery that is very close to the university in the Royal Docks. We developed an interlocking structural slab prototype, which you can see in the image. Started to look at stereotomy and the ancient legacy of stone structures, from arches to vaults into flat chambers or flat arches, and looking as well as dry stone interlocking systems from South American, Mexico and Peru structures, and how these elements, just by geometry, without the need of mortar and without the need of additional elements to connect the stones, they achieve structural stability. And we came across the work of a French engineer who developed a flat vault design. It was called the Abelle vault. It was done in 1699. And it was a vault that was just playing with geometry and interlocking strategies to create a flat slab or a flat ceiling that without any mortar will stay in place just by applying compression on the perimeter. So we replicated the system using Sugarcrete, bound with silica binders. One of the main challenges that we had is that we needed to achieve a compressive strength that was higher than what we had at the time. We calculated with the engineers from AKD2 that we will need to reach 5 megapascals of compressive strength, and we were down at 1 at the time. So we worked with colleagues in the Sustainability Research Institute, material scientists, to find new binders and to find new compositions that could achieve that compressive strength that was required. And we managed to get to 5, which we are now trying to get back into that level with formulations that can be more cost effective in India, but was enough to do a slab prototype that could span 3 meters times 3 meters without intermediate support. You see here the pieces that compose the slab. So they are truncated pyramids and they have perforations on the perimeter. You can see the holes that are made there, and then there are metal rods that then will come into the perimeter and will compress all the elements together. We built it at the university using as well 3D scanning facilities to assess the shrinkage of the material. All materials that have curing process into them, they have different degrees of reduction when they cure. In our case, we were quite interested to see if there was any reduction depending on the fiber that we will use. So we tested with hemp, we tested with typha, we tested with sugarcane to see the reduction of each one of them. And then we compare it with the initial 3D model that we use to create the original pieces. And this is us setting it up together. As you can see, we are here placing the metal rods. There is a very good video on the website of the timeline process if anyone is interested. And then we place a number of flat elements on the corners that would allow us to then, with a very simple tools, tighten up the perimeter until we achieve the right compressive strength to keep all the pieces together. This is the size that we tested was 1.2 meters times 1.2. We calculated that it would span 3 times 3 without the support in the middle, and we tested it ourselves. So we tested it first for compressive strength with machinery in the lab, but then we just stood on it after finishing the workshop. This is the result of a 2 weeks workshop process. So as you can see, it's quite an intense process of making, and this is the final day when we typically do a day of photographing and celebrating the work that the students have done, and then there is a reporting process that takes place in the upcoming month. I think that it was for us, this project was a very good collaboration with Grimshaw, even though it didn't end as we will have hoped. For it, was we managed to finish in September, October, with the idea that it could be exhibited in the Royal Academy that year, which went to the exhibition of the Royal Academy. We published it initially on the scene, and thanks to that publication, it got quite a lot of media repercussion, and it reached outlets in several languages across the globe. Thanks to that, we got contacted by our partners in India. So the work that you will see in India later comes from this work that we did here, which didn't leave the university. We didn't explore how this could be used with partners anywhere in the world, but it gave us enough support and enough momentum to actually continue. And because it was very well photographed, very well documented, it was a geometry that was very appealing, it allowed us to reach more people than with the samples that we had done previously in the lab. However, we didn't negotiate properly. There was the first collaboration that we did with a large external partner, and we didn't have any agreement on intellectual property when we started, which is the first thing that we do now. The first thing that we do now is to sign a non-disclosure agreement, as we saw in the diagram that Alan was sharing, and to discuss what is the background intellectual property and the foreground intellectual property. So what do we put into the project ourselves, and what's going to result from that project, and how do we negotiate it? But here we didn't do it, which meant that when we came to that exhibition in the Royal Academy, which is one of the most prestigious exhibitions in London, we realized that Grimshaw didn't credit us in the exhibition, which for us, it was obviously not good. For the university, it was also not good. And we asked them why was that the case. We saw other examples of collaboration where all the partners were accredited. There was not a clear answer. That was followed up by another couple of issues where intellectual property was not properly or even just credited. So we kind of stopped the collaboration with them, which was a pity because we thought this could have had a long trajectory. But it made us learn as well that it's important, whoever you are collaborating with, that you agree very clearly how you are going, what are the objectives, and what is the contributions that each one would do towards the project. It made us also aware that initially we tried to patent the material and the system. Tate and Lyle covered expenses of the initial searches that are required for patenting. And we realized as well, as Alan was mentioning, that that was not the route that we wanted to take, that first of all, it will need to be country specific. So it will be very difficult to implement in all the countries where we were collaborating or where we were aiming to collaborate. And secondly, it was depending on the formula. So as soon as you change anything on the formulation, which we are constantly doing because we are looking always to improve and to contextualize the formula to different contexts, then you need to apply for a new patent. So instead of that, we secure the trade secret, we secure the trademark, which we did when we were doing this project. After we realized that the relationship with Grimshaw was not what we would have hoped, we decided to trademark it as quickly as we can, and we managed to trademark it very easily for the European Union and for the UK, and therefore protect to some extent the intellectual property of the project. That led into more knowledge on how to collaborate, and through a European fund, the EU Worth Partnership, which is a fund that supports entrepreneurs and designers to team up with institutes or universities to develop products together. And through that partnership, they are already having a policy or a system on how that collaboration should happen. So when we saw that opportunity, we realized that that was the step that we were missing from before. How do we agree from the beginning on what are we doing and what is the result? And this was a much more successful collaboration for us, even though it was with the designer from Barcelona. That is just is actually a team of two people, a very small firm doing very good design in product and interior, but not compared with the budget and the capability of Grimshaw. However, for us, it's been much more successful as a collaboration. And it has resulted into an acoustic and thermal panel that we are now manufacturing for the European market, which is the one that you see in the image. The firm is called Bagaceira. It comes from Portuguese. It's also related to bagasse, the byproduct of sugarcane. And it was started as a workshop, a construction wing workshop, where the founder of Bagaceira came to London for 2 weeks, was working with the students, developing a prototype, and then took that knowledge back to Barcelona, where they are based, and started producing locally in the south of Spain. It was also supported by Sandy Brown, acoustic consultants. We always try to bring industry partners that are experts on particular topics. In this case, they were assisting with the acoustic performance and the reverberation improvement that these panels could achieve, and they were fundamental to the development of the project. This is the prototype that we built. On the left, you can see a finished element. It was made with molds, which we have here at the moment. They were at our back here in the incubator space at the university. And the molds were designed in a way that you could disassemble them and assemble them again, creating geometries of different lengths. So all these geometries are made with only 2 molds, even though they have different lengths. Just by disassembling and reassembling the molds and then bracing them on the perimeter, you could achieve different sizes, which creates kind of dynamic geometry. The geometry is curved, as you can see, which means that when you unfold that geometry, you get much more surface than if these were flat panels, which is obviously beneficial for improving acoustic performance and for improving the reverberation time on internal spaces. And we did it, the mold that you see on the right, we did it here at the university with CNC facilities, and then we casted a set of panels as a test internally before the cast that you see on the left. These are some photos that we took on the process. You might have noticed that the photos that we are showing, they are quite curated. They are all trying to highlight only the piece and the essence of the project. We typically collaborate with students of photography of the University of East London. So we do a cross-disciplinary collaboration where they join the 2 weeks workshop and they take photography of the architectural pieces, and we very often get them published in DC and Arc Daily. So it's a very good exposure for photography students that are in their 4th and 5th years of their masters. And these photos are trying to highlight the process, like all the steps that we took. We use mineral pigments, clay-based pigments, to coat. Some of them were coating the material in these 3 samples that you see at the bottom. The first one is just a render, which was a lime wash with the color applied to the surface, whereas the second and the third one, they were mixed with the fiber itself, just to create color going across. Both of them work quite well. We are more inclined to test what happens with this option, so you can control more the finish and the color. And you can see here all the components that we put together. This is the silica base binder that we use for the mix. These are the fibers of bagasse as they come, and this is the bagasse itself, dry, once you have cut it. Some samples that we develop, the samples have different sizes depending on the testing that you are going to do. This is the testing that we do for reverberation at the laboratory, and this is the testing that we do for thermal that tell us what is the conductivity, the thermal conductivity of the material. And all these samples and all this testing was done as well as part of the construction workshop with the students. Following the workshop and following the collaboration, we were invited to take part in a real estate forum in the south of Spain, a region that is very touristic. It has a high demand for construction due to the good weather and being very close to the Mediterranean Sea. And it has also a tradition of growing tropical climate crops. It's called the Costa Tropical, the tropical coast in the south of Spain. And they used to grow sugarcane in the region. They had a very strong industry until the 80s, early 90s, where, because we entered the European Union, then the quotas of sugar production changed, and most of the sugar industry closed. There are still some producers. This is one of the last farmers that are still producing sugarcane in the area. In this case, is for rum production, not for sugar, but this is still actively planting sugarcane, and they have byproducts. And there are a lot of crops that are there. There are a lot of fields that are still having sugarcane from the time when it was growing, and it's quite interesting because in their case, sugarcane, the way they use it, below a certain line where the soil has salinity levels that are too high to grow other crops, it helps through rotating the crops. It helps improving the soil quality because it reduces the salinity of the soil, and then it allows that the year after they can plant potatoes and different crops. So there is a lot of interest in reintroducing sugarcane with different values, this time looking at it as potential construction material. And we are still developing that project forward with the community and the municipality of Granada. One of the mills that was traditionally producing sugar is now a museum. They are retrofitting the mill into a museum that talks about the history of sugar in the region, and that talks about what is the future of the sugar industry. So we decided to, once we finished the collaboration with the students, the installation was exhibited in the Milan Design Week. And after the exhibition, we decided to donate it to the museum and to test the improvement of performance in one particular area in the entrance to the museum. So if you visit Granada, you can see the installation there. And this is how it was installed, using metal profiles that were mechanically fixed to the wall, and then the panels were fixed to the profiles themselves. And I think that in like this, maybe to summarize, the value of that collaboration was as well that we discover the European certification process, which was very similar to what we were doing in the UK before, but we discovered laboratories that were more willing to work with us and that were able to understand better because they were working with bio-based materials a bit more extensively that we were working in the UK, and to understand better how the testing will need to be done. So it opened up a set of new testing that we developed with them that then led into improving the formulation of the acoustic panels, which we are now using for with our partners in India as well. So what we learn from one region, we always try to implement it in others. And that led us into the next project, which is now related to our collaboration with India, which started from the first project that I explained. So once we finished this lab and we published it on this we were approached by Chemical System Technologies. It's a company that is based in Delhi, and they have a very extensive network within sugarcane mills in the country and also in other areas on Asia, because they provide machinery. So they are the ones that set up the sugarcane mills, they set up the refining process, and they set up the milling process as well. And therefore, they were very interested to potentially introduce this technology to different mills. So rather than having them a centralized facility where they produce, team up with different mills so they could produce locally the blocks themselves. The project was supported by UKRI Higher Education Innovation Funding, which support knowledge transfer and commercialization within universities. And the land where the school sits was donated by the Ministry of Education in India, and it sits in a college in Noida, close to Delhi, which is called the Panchsheel Inter College, which are now partners of the project, and we are actively collaborating with them in different areas. We co-designed this, the design of the school with students from the University of East London and students from the School of Planning and Architecture of Delhi. And the idea was to design a proof of concept, a prototype that could be then implemented in other areas as a
Oops. I think he was cut off. I think you're muted, Alan.
Yeah, no, I'm not in London, so this
Oh,
is maybe
okay.
a London problem.
London problem.
They've all disappeared. How interesting.
Yeah, I think it's the line issue. But yeah, I think
he got disconnected.
hi, Michelle.
Yeah, the nerve center brain of UEL has gone to sleep suddenly. So
Hi, Michelle.
I can finish off the lecture if things don't appear in a moment or two. So.
Hi, Michelle.
He's coming back again.
He's back.
Yes, apologies. We had some issues with the battery.
Right.
Let me just go back to my speakers. Can everyone hear me okay?
Yeah, it's all right.
Yeah, you're good.
Okay, perfect. Let me just share my screen again. Yeah, so the project was also aiming as a prototype to be monitored and to be used as a tool to learn more about the performance of the material. So it had a 12-month monitoring scheme, which we are now getting the first results of the data that we developed. And in this case, the brief that we had for the students and for ourselves was to design a block. So it was the entire construction week effort was by default was first to design a one-to-one block that would be adapted to the context of India, of what we wanted to to achieve, and at the same time, in parallel, design a prototype for a school that could be built using that block. We used a mix of bagasse and hydrated lime. So we put two components together, which was slightly different. So this is mineral based rather than silica based. And the idea was to create a block that would have a slightly simplified version from the interlocking blocks that we did for the slab, but still have an interlocking component into it, which working with the engineers from AKT2, they suggested that thanks to that interlocking, if it was happening above a certain height, we could improve the seismic resistance of the wall in case of movement of the wall on earthquake areas, which is where we were working in India. We are now working with partners in Pakistan, which are also looking at alternatives with interlocking systems. So we think that having some degree of interlocking that can improve the seismic resistance of the wall and also minimize the amount of mortar that is required for placing the wall together. We thought that was an advantage to have, and it didn't interfere with the resistance of the wall. We developed two blocks, one that was equivalent to 2 bricks, which is the one that you see at the top, which was 230 times 230 times 75, and then a corner block that allow us to turn around without cutting or without generating any waste on the blocks, which was the equivalent to 3 different bricks. We tested the corner, so this is what we built with the students at the University of East London, and then we built a set of drawings as a guidance on how these blocks could be implemented into a larger wall, and how, if you were within a module that is set by the size of these walls plus the mortar that is required to put them together, you would avoid any cutting of blocks when it comes to windows, openings, or lintels. We developed a lintel prototype as well, changing slightly the formula so we could create something that had good resistance on a 3-point load testing, which we did here in a bit of a homemade way, just adding a weight in the center. And we managed to achieve an improvement into the resistance of these lintels by first we tested including an inclusion of a timber element in the middle, and we also tested including a Hessian mesh on the underside, which only the Hessian mesh alone increased the capacity, the loading capacity times 3 compared to just the version where we were having the Sugarcrete lintel. We designed this as the window opening, so we could have a lintel at the top, a lintel at the bottom, and then just resolve it with blocks without any wastage, because we wouldn't need to cut any of them just by using the regular block and the oversized one. The idea was to create a section using a clerestory truss that would allow for high-level ventilation, and then have windows that would open at the bottom and at the top, so the fresh air could come to the inside. We allow for verandas in both north and south orientations to protect from direct sunlight and direct weathering, and also to create external areas for playing for the children. In summer times and summer months, which are starting earlier and earlier in India, the rooms, especially the ones that are higher level, they have no insulation, and very often they become unusable. We are now looking into retrofitting strategies for some of these rooms in many schools in India. So the idea was to prevent and to minimize the overheating as much as possible. This is the process. This was already 3 years ago when they started the building process. We visited a couple of times during the construction, and we spoke to the master bricklayers that were starting to use the material, and it was quite beautiful to hear that it was very easy for them to embrace the material and to change from bricks or concrete blocks, which is what they are used to, into the Sugarcrete blocks. And the building was built in the same amount of time that it would have required if it was made with bricks or with concrete blocks, so it was no delay on the construction process. Some photographies comparing the back using concrete at the stone with softer Sugarcrete at the front. And this is the finished school. We decided to apply render internally to a certain height, and then to keep the wall exposed on the upper level, and then to apply plaster render externally. We describe plaster rendering with the lime plaster externally and a clay plaster internally. They did internally, they didn't have any issues. Externally, it was very difficult for them to find labor that was able to apply lime plastering, even though lime plastering was what was used in India traditionally in all historical buildings. But it's a trade that is been lost almost in one generation of use of cement. So we team up with an architectural firm that has their own team producing and creating and rendering because they are specialized on earth construction, but they didn't manage to transfer that technology or that information to local workers. So at the end, they ended up rendering cement, which is not what we would have recommended, which means that the performance of the wall is probably not as good as what we would expect because it's slightly covered on the outside, yet the monitoring results that we are getting are really promising. The school is being used to run workshops on green infrastructure, bio-based material, air pollution, and the use of potentially agricultural waste for construction. And it has an active agenda where kids from different schools, not only from the college where it sits, but from different state schools, they come to learn about the project, about the material, and to engage with the building. We have a team that is working in the college, and they are getting all the information in terms of how people feel when they use the building and how is it performing in terms of acoustic, in terms of thermal. So we are monitoring all the data that we get. Last time we went there, when we officially opened the building, there was a music performance by the music director of the college, and he was really impressed by the quality of the sound. They are used to rooms with no acoustic consideration, where concrete blocks and bricks have been used for the walls, and ceilings are either using plasterboard or directly reinforced concrete, which are having very high reverberation times, between 3 and 4 seconds. We are in Sugarcrete around 0.4, 0.6 reverberation time, which is almost the acoustic studio quality, and he was really impressed by the acoustic performance that we were achieving. We wanted to share some preliminary data of what we are getting on the air monitoring results. So once we finish the building, we install 3 monitoring sensors, one inside the building, one outside the building, and one in the same complex inside the school that is using conventional materials, concrete blocks and reinforced concrete for the slabs. And we are comparing different parameters to do with air pollution and to do with microclimate. Air pollution, we are reviewing PM2.5, PM10, CO2 and compounds. And then for microclimate, we are looking at temperature and relative humidity. And there is a strong attenuation, especially for PM particles, around 30% attenuation compared with external conditions, and 20% attenuation compared with the control room, which are suggesting that the material is having a filtering effect on air quality, which we still don't know why is that happening. We have brought a couple of blocks from the building back to analyze it in the laboratory. The hypothesis is that the surface of the material is trapping some of the PM2.5 and PM10 into the surface itself. So as we were mentioning before, the material has the capacity to breathe. So it has very good moisture buffer value, which means that it's able to absorb humidity and then release that humidity back or either outside or back into the room when the humidity level changes. And that effect might be getting some of that compound, which is generated externally, entering the building and then being trapped by the blocks. Likewise, there is a very good attenuation of TBOC compounds and a very good reduction on humidity levels, which was something that we were expecting. And this leads to the last project that we wanted to share, which this is a photo from our trip to India a couple of weeks, already 3 weeks ago before the Easter break, which builds in a collaboration that we are doing with the Pariatam Foundation in India, in Hisar, in the state of Haryana. Last year, we worked with students from Master of Architecture to design. Their brief was to design a community center for the foundation. The foundation is currently using two different centers which are rented. So they have acquired a site and they are looking into building their new foundation building in the next year. And they saw our work on Instagram, and they saw the work that we were doing in India with chemical system technologies, and the founder, which is a civil engineer transformed into kind of NGO community director, approached us saying that he wanted his new building to use the material and that he wanted us to visit them. And since it's been an incredible collaboration. We have the students designing the center, and then we selected some of the designs to continue into a holistic project that we developed in collaboration with local architects from Studio Shunya in Delhi. And this wall that you see there is a fragment of a classroom from the building that we have designed for them, which hopefully will go to site in November. Since we started the collaboration, because of their association with the University of East London and using a material that is new and innovative, they have managed to fundraise enough money to buy the sites. So they were missing 3 sites that they have fundraised thanks to the collaboration that we have done with them. And now they are using this wall, and they are using the fact that we are involved into the project to convince people locally to support the project and to get enough funds to get started with the construction. These are some photos of how the foundation looks at the moment. This is the building where they sit. This is the welcome ceremony that they did for Alan in the first visit. And they work with the underprivileged communities and children that left education earlier than they should have, and they bring them back into the education system through the foundation, particularly girls, which are since early age, they are kept, they're encouraged to stay at home and to help and to work from inside the household, and the community is kind of acknowledging and embracing the work of the foundation. And they have already 100 children that are going back into education through the work of the foundation. They are hoping that the number would grow to 150, 200 children, and that's what we are doing for the design. So this is some visuals of the design that we are putting together started with the students from the university, and now continuing as a collaboration with the local architects. It uses wind. Both the plan and the sections, they were designed to embrace as much as possible the prevailing wind direction, which is coming from a water reservoir that is very close to the site, which means that the wind will come slightly cooler than the wind that they have currently in the area. So the plan access is designed in a way that optimizes the wind flow around the central yard, the central atrium. And then the section uses a set of wind chimneys that are located on the demise wall towards the north of the building, which means that you can achieve cross ventilation through a stack effect in all the rooms, both the ones that can achieve cross ventilation because they are open on both sides, and the ones that are using the wind chimney to create that effect. The idea is to represent and embrace a number of vernacular structural systems that have been used for centuries in the areas, such as vaulted ceilings and rotac domes, and do them using, when possible, Sugarcrete to replace the clay bricks to create these structural elements. And to demonstrate that this is possible and how we will build it, we organized a workshop with the community where we invited all the members from the Pariatan Foundation, plus state schools, especially that were targeting groups of girls that were coming to join the workshop. We did it over 2 days. The blocks were manufactured before the workshop by our partners, and then we gave the brief to the students to co-design the installation with us. The idea was to build 1/4 of one of the classrooms that we have designed for them, and build it with the community. So we said each children needs to place a block, and that's what we did. We started building it ourselves using lime mortar and the blocks to create the wall. And we encourage all the children of the foundations to actively be involved in the workshop. Then we were joined by two female-led architectural practice based in Delhi that are experts on clay rendering and lime rendering, and they apply two different renderings: a lime render on the outside, and then a clay rendering that is supposed to be used for the internal surfaces of the classrooms. And we did a workshop where the children of the foundation did some drawing, and then by adding clay on the wall, they created a drawing that was personal for them. These are some photos of how it looks. We tested the Yali screen on the right as well by creating spacing, so we could use it for ventilation, high-level ventilation, which is what we are going to be implementing in certain areas of the toilets. And then this is the process of making the wall. We built initially a base. So we always recommend that the material is raised above flooding level or above heavy rain level. So we raised it to 450 millimeters, which was also the height of the bench. So then that brick wall transformed into a bench at the end of the installation. And then above that level, we started placing the Sugarcrete blocks, which we wanted to demonstrate as well that they could achieve curvature just by doing a small cut on each one of the blocks. That was quite easy to do on site. You can drill through the blocks, you can cut them, and you can very easily adjust them on site with very little waste. And you see there one of these ladies that we did a couple of lectures following the installation, and the questions that we were asked were extremely intelligent. They were very curious about knowing the material, but also about knowing how do we fight perception and how do we fight preconceptions of bio-based materials being weaker and not performing as well as traditional brick or cement. And it was a very good conversation. I think that the fact that we built it with them, it meant that they embraced the material much better. The first day at the beginning when we started, everybody was a bit hesitant, but then after a couple of hours, both the construction workers that joined us and all the children and members of the foundation, they truly embraced the process, and they were very keen into placing a block to create a wall built by the community. And I think that's the end of the presentation from my side. I think we have some time now to take some questions from the audience, either here in London or from our partners.
Thank you, Alan and Amor. I think it's a really interesting presentation, and I personally have learned quite a lot. Yeah, I think we'll open the floor to any questions from our students or even from those from the UK.
Yeah, I think I will go first. I mean, it's right before I ask a question, I think I should give an introduction for this series of lecture. I should have done that in the start of the lecture. Right, so most of the audience here are all from UCSI. So most of them are all in year 3 and year 2. So the idea that we have right now is that we have signed an MOU with UEL, right? So everything is legit. So we're trying to have a series of lecture between us to build up a workshop, a summer workshop towards, I think it will be mostly towards August before our semester starts, where where representative from UL will come over to Malaysia, and then we could have a workshop to do something. So it's a beneficial for our students and also for our lecturers. Also, for your information, we did run a collaboration before last year. Keta and also Charlotte from UEL came to Malaysia, and we had like a 2 to 3 days workshop to work on some casting, and also they were involved with the exhibition in London, where we test on Shako and also the place at Sepetang, which is in Selangor. So it's going to be a series of lecture. I think it will be happening once a month, I think. So now April is from UEL. Next month most likely will be from us. So we have like 2 to 3 lectures before we kickstart the summer workshop, a physical summer workshop, by the way. It's not online, it's a physical thing. It's happening in our MIG lab here in block E. Right. Okay, now back to the question. Okay, so thank you again, Alan and Amor, for your sharing. The only thing I want to ask about is that you were saying about most of the master student in year 1, they will have to do a prototype of your Sugarcrete, I suppose. What happened then? I suppose, do they need to, follow up to do their Sugarcrete ideas as a group work into their individual design project? Do they have to do that? Is it a compulsory thing for them to move over towards their individual, or it's going to be like one-off exercise on the Sugarcrete project?
It sort of depends. What we like to do, we were very democratic, right? So you may remember back in the day, we would offer a range of workshops for people to kind of vote on. So we end up with groups of students that want to do that particular workshop. So we usually offer, it depends on how many students we got. I remember one year, probably back in your day, we ended up with 13 workshops in one year, which was completely absurd, but we all had a good time. We usually run about 4 to 5 workshops. Some of those maybe that's a translation. The key thing is that they are, some of them are research based, so we would offer some Sugarcrete workshops. Some are nothing to do with Sugarcrete, so there's a range of workshops. But what we find is that these kinds of activities, particularly engaging with the material science, kicks ideas off in people's heads. They're new to UEL, they've come in to do the master's program, they've done a degree often somewhere else, and so it's a way of working with a team of people, getting to know each other, becoming really good friends, becoming interested in things that they might not necessarily have been interested in before, and they tend to hold on to that knowledge, and then they work with that in their own projects. Sometimes Armand might set a kind of Sugarcrete based project, as he did in India. He took the students to India to work on the Pariatan building, but often it's just about putting new ideas into the new cohort's head so that they can begin to kind of filter some of the issues that we might throw up, which is why we're always talking about material science, social science, architectural design. We try and put all of these things together so that people can get a wide range of experience, and as a group they then submit a report which is then part of their technical studies grades for the year. But yeah, it just happens at the beginning of the year, beginning of their year 4, or the first year of their masters, so that they can really just kind of absorb the value of getting your hands dirty and of making technical material decisions. So that, you know, back in the day we didn't have computers and CAD. It was a lot easier to kind of feel a physicality of stuff. These days it's very easy to get lost in Rhino. So this is part of that kind of process of reminding everybody that materials exist in the world, as do we, and ultimately that's what we have to make work.
Right. Yeah, and now I remembered. I remember that we did a fabric concrete curve with all the fourth year. Yeah, now I remember. Okay, another question is that have you ever thought of trying here in Malaysia? Because we do have a lot of sugarcane, right? We do have a lot of plantation. If in fact people like, you know, we do have the thing called a roller that we can, you know, make raw sugarcane juice. Then we can just drink it. It's part of our sort of like a drink that we can drink usually during the hotter day, because sugarcane for us is like a cooling, sort of like cooling drinks. So yeah, so we do have a lot of shops here and there that do raw sugarcane, raw sugar juice from sugarcane. Then you will have that material that you want to do your bricks. Yeah.
No, I mean we've come across people who've organized setting up, collecting that stuff. They do the same in Brazil. They do similar in Africa. So it's a you know, but it generates quite a lot of bagasse, and the people who are doing that on the street or just selling, they've got nothing to do with this stuff. They don't know what to do with it. It's just waste.
They just throw away.
So collecting that on a kind of citywide scale, you'd end up with quite a lot of it every day, right? And so that then can become a product. So it's trying to kind of introduce the idea of it, because sometimes it can be a very simple technology. Then people can just start being entrepreneurial about it, and they can go, well, I've got this huge garage full of bagasse waste every week. Why don't I just mix it this way and make these products, and then I can sell them for much more than I'll sell my drink for, weirdly. So I think it's not an exclusive process, it's an additional process. Right.
I mean, back here in Malaysia,
it's actually how we started in London as well, collecting from sugarcane juice in the street markets. Because the first samples that we produced was doing exactly that.
Right.
Your question, we don't have any partners at the moment. I don't think we have spoken to anyone in the region yet. but maybe this can be the beginning of it.
Right. And also for information, in Malaysia, we also use sugarcane as part of our praying. You know, there'll be it's a Chinese culture thing that's I think once a year, we have this huge festival that they will use sugarcane to pray to the gods, stuff like that. Yeah. Then they will
Didn't
just
know that.
then
Didn't
will
know
just
that.
then they will just discard it, or they will just make it a juice and drink it. Yeah. Okay,
It's a
I think
project
right, I think I'm back to Scarlett. Is there any question from the floor? Anyone?
Yeah, I think I have a question myself. Because I think the development was in a brick form, and I can see the kind of applications and the ease of replicating all of this. I was wondering, like, is there a possibility where it's perhaps done in like a larger scale? Like, is there a limit to the size of the brick, or is it just limited to the size of the mold? Could it be done perhaps like cast in situ, where you add the bagasse into the mix itself, or is it just a brick form?
No, I mean the brick that we used initially in India was more to build with the way they were working and the way they are laying blocks and the way they transport it. So being able to produce a lot of blocks beforehand, bringing them there and then building a wall relatively quickly without the need of adding formwork to do the casting. But you could build it in the same way as you do with ramp earth. If you didn't want to pre-made the blocks initially, you could just cast it in situ and then build it up. But it will add the additional complication of building the formwork initially and then waiting for it to dry before you move to the next level. So we thought that creating the blocks, letting them cure in a facility that is local to where the bagasse is located, and then moving the blocks from the bagasse mill into the site was a better strategy. Also, moving the bagasse without being mixed is quite difficult because it's highly flammable. When we coat it with the binders that we are using, is fully fireproof, and you can move it very easily because it doesn't produce dust. But when you have bagasse in the raw component, it's a mix of fibers and dust. When you visit a sugarcane mill that is in operation, it's continuously snowing bagasse dust. You cannot breathe when you're inside. And it's a material that when you transport it, it's producing a set of complexities. First, the volume is massive. So when you see the trucks that are transporting the bagasse, they have this, I don't know if you have seen it in your country, but they kind of oversize from the cantilever from the size of the truck. They have issues on speed and they have issues on fire, so they need to be very careful on how they transport it. And then when you store it inside, it's also not easy because it needs to have the right humidity and it needs to be protected. So we thought that rather than dealing with the complexities of transporting the raw material, we would rather already transform it into a product that can be very easily transported in a safe way and therefore avoid those complexities. But the geometry itself, it can be a larger block. When you look at hempcrete blocks, they are quite oversized. They are typically 3 or 4 times the size of the bricks that we are using, which means that they are heavier, so it might not be so easy to install, but you will build quicker. So that could be another alternative. We are now looking at panels for retrofitting internally, which are a bit larger and a bit thinner, so they can be installed vertically and either applied with a mortar or mechanically fixed to walls. So no, the geometry is not set. We have just developed a number of geometries because our partners wanted explore that particular application, but that can be adapted. It's more the material itself than the geometry or the product.
Mm. Thanks for the explanation. I'm asking this because perhaps in the future I have a project with rivers, and we're doing like a master plan for the river, and we wanted to sort of create elements that would sort of populate the riverside to allow people to enjoy. So it's a small-ish project that I'm bringing my students into as well. So I was thinking that if we could actually change the form of it, or rather than just having it in brick form, could that be different ways of expressing this material? Yeah. But yeah, thanks for the explanation.
We had an inquiry to make grain silos in South Africa. So they make them out of brick, and then they get very humid inside. The moisture can't get out. They go moldy. So making curved blocks of a certain diameter that can make these big cylinders to take the grain is, yeah, sure, we could do that. So in a way, it's what you can kind of do with precast concrete, you can kind of do with Sugarcrete. And what we found is like the addition of kind of small timber elements or Hessian to kind of control the surface tension gives us the ability to kind of treat it almost like small scale concrete elements. Obviously, we can't make bridges out of it, but it's for the kind of purposes that you're thinking about. You know, you could make a piece of meter and a half long, could be this thick, this wide. It's just down to how you then transport it. But yeah, we found that it's very flexible. So yeah, I think it's pretty useful.
Amazing. Thank you. So yeah, let's open up to the floor. Any more questions from the floor? No questions. Everyone understood everything perfectly. Amazing lecture. So everyone understood everything.
Perfect.
Good.
Last call, guys. Anyone? No? Oh, okay. We have a question from the chat. So it talks about the humidity. How does it deal with the humidity?
Okay, I mean, the moisture buffer value is the kind of technical measure of that. And it's extremely good. So it allows vapor, moisture, airborne water to go through the material. And so it sort of acts slightly like a sponge, but then it releases again. The minerals create a series of kind of pockets or pore spaces through the material. So the material doesn't absorb water by swelling like timber does and then shrinking again. So it's not trapping the water in cells, which get bigger. It's actually holding the water within open cell structure within the block. So the block is stable, but it can take up water and then release it very, very quickly, because there's a kind of capillary action where the water through these kind of tiny channels in the material can then, as they evaporate to the air, they kind of pull the materials along with them to evaporate. So you get a very interesting kind of lime-based action, which is, you know, has been used for centuries, but nobody kind of knew exactly how. Now we've got electron microscopes, we can actually see how it works. So it's a whole chain of water that enters the thing and then can leave it very easily and quickly, because it drags the water out as it evaporates to air. So as long as you don't render it in cement, which is unfortunately what they did in India, you are able to have air moving both ways depending on kind of temperature and wind speed. So yeah, it does absorb very well, but it also releases it very well and therefore dries out very quickly.
Thank you, Ellen. I hope that answers the question. Yeah. Thanks, Shay, for the question. Yeah, and I think with that, we have sort of concluded our first lecture for our series. Thank you so much to Alan and Amor again for sharing with us your knowledge, sharing with us the technology. And yeah, thank you everyone for joining in today as well. I will be sharing the recordings so that everyone can sort of look back and refer to it as well. And hopefully we'll have a part 2 to this. Perhaps when we go into a little bit more technical details, but we'll arrange with that soon. And with that, thank you once again, and I hope that everyone has a good rest of the day.
Great.
Thank you,
Thanks
everyone.
very much, everyone.
Thank you, Amor.
Good to see you again.
Good to see you, man. Bye.
Thank you. Bye.